on the 2D rotation of Bohr model for non-equilibrium orbitals. Some of the equations I used this first equation, which converts angular momentum to polar coordinates, so we could plot the angular momentum in a way that we can understand it on the Bohr model. And then the second equation is it shows the difference between kinetic and potential energies and how they're related to the Hamiltonian. My methods, I used a MATLAB code written by Dr. Killen, and then I added the commands to automatically save the videos so I could upload those to YouTube later, so I can add them to my presentation. I changed the numbers of nodes and then reran the code so we can see how the nodes changes the angular momentum of the electron movement, and then we analyzed how those nodes affect the movement. So here is just a polar standing wave, and the red line on there, they're all kind of overlapping, but just imagine with me and we'll see them on later plots. The red line is the real part of the wave function, and the green line is the imaginary part. And then the blue line is the combination of those, which is the red line squared plus the green line squared and the absolute value of that. And then the blue line shows the stability of the electron in each node and orbital. So if the blue, later in the videos, if the blue line is pretty much unmoving, then the electron is going to be more stable. And if it's moving, then the electron is not stable and will quickly change so it will become more stable, and then it's less likely to undergo a transfer to a different node. So here's the first node. I ran it with 1.56 nodes, and you can see the very quick movement of both the red, green, and the combination of the two in the blue line. So when there's not an even integer number of nodes, then the electron is a lot less stable, and it's going to try to get back to a more stable state. And then the second one, we did 2.02 nodes. So clearly those movements are a lot more stable, and the combination of the red and the blue the red and the green makes the blue line unmoving. So this electron is pretty stable in its condition. And then moving forward, here's 2.64 nodes, and this is unstable once again because it's not an even integer. And then finally, here's 3 nodes, 3.01 nodes, and this is stable once again, and that blue line is unmoving, so it's happy in its current position. And then, so conclusions for this project was as the number of nodes change, the radius from the nucleus increases as the number of nodes increase. If we go back and just compare the radius of each of these, it clearly gets larger as we move forward, and finally the largest at 3 nodes. And then, as I mentioned before, the even integer values create smoother movements and more stable atoms. And then the value of orbitals is 2 times the number of the nodes, so there's 1 positive and 1 negative for each node. And then finally, we looked at limitations of the Bohr model, so it's only a 2D model, so it can't show 3D movement, and that led to the lack of understanding of what the electron would do in a 3D space. There's some references in there.
Okay, thank you, Amelia. Again, the presentation is open for discussion.